Thanks for coming. I'm Rafał Studnicki. I work at Erlang Solutions, as Bartek said. And for almost 2 years now, I've been writing code at Grindr, mostly Erlang and Elixir. And well, I wanted to talk about some work we've done quite recently that focuses on meeting certain SLAs, or actually service level objectives, to be honest, that we've done on some backend services. And well, before I'll tell you how we implemented it, and if it even works, if it at least works, let me just very quickly tell you what was our motivation and what problem we were trying to solve. But first, let me ask you a question. How many of you know what Grindr is? Quite a few people, okay. So if you don't know what Grindr is, it's, well, basically it's a dating app. The user base, it's more or less, it's slightly over 3 million daily active users. So currently it's mobile only, so if you want to check it out, you can download it from the App Store or Play Store. But if you look at Grindr's backend stack instead, you would see that it mostly consists of Java services. You don't need to look at it now. You would see that it consists mostly of the Java services that are handling clients' API calls. But apart from that, there are some other services handling some more soft real-time things like chat in Erlang or presence in Elixir. And well, because almost every single thing that we do at the backend initiated at the client, and the client is waiting for the response. And at least for me, there is no more annoying thing than this spinner spinning, waiting for the response in the app. We want to make sure that this response is generated very quickly. So that's why we focus on observing these tail latency graphs all the time. And trying to optimize that. And if maximum response time is below 50 milliseconds on our side, that's great. So for example, let's take a look at this very, very simplified diagram, architecture diagram. So let's say we have a user service. User service that handles some information about users. It has its own DB. And it happens to be that the present service is its consumer. From time to time, it needs some information about users. And so now imagine this scenario when the user services database slows down for any reason, so that it cannot process all these present service requests quickly enough. What can we do then? Well, the very simple approach, a very naive approach, is to just put a queue in front, being the user service, and queue all the requests. When the slowness disappears, just process them. But the queues, as any physical thing, are governed by some laws. They're described by the queuing theory, but there is one very simple law from the queuing theory called Utilization Law. It's very simple, it's very basic. If you just divide the rate of incoming requests divided by the rate of requests in the time unit that you can actually handle, you get the utilization rate. So you're getting 100 requests per second. You can handle 200. The utilization rate is 0.5. Just think the load metric in the operating system.
What are the units on each of those?
It needs to be the same unit. It doesn't matter. I mean, both need to be in the same time unit. So
I'm guessing incoming rate of requests is number per second.
Right, but
Service rate is a time. You multiply the two, you get a number.
yes. So 0.5 is that we're utilized at 50%. Right?
Ah, so utilization rate will be a number between 0 and 1.
Yeah.
Okay.
So yeah, as I said, very simple.
Lambda does not denote function abstraction.
Yeah, no. Right, so let me just visualize it very quickly. If we have utilization rate 0.5, so on this graph, the purple line, I mean, on the x-axis, it's a 2-minute simulation. X-axis is time, y-axis is a queue length. We have a single queue. Purple line is utilization rate 0.5, so we can handle twice as much requests. You can see that this queue length is mostly 0. Sometimes it's up to some number, but it unloads very quickly. The reason for this to be higher than 0 is that it was sampled at different times. Now let's take a look at this blue-green. It's green on my screen line. Now the utilization rate is 0.9, so we're coming closer to 1. You still can see it's stable. It's slightly higher because we do more stuff. So the queue length is slightly higher, but it's still stable. Now, if this utilization rate grows above 1, so if it's 1.1, for example, this will look like this. So the queue length will grow infinitely with time. And that's pretty intuitive because we enqueue more requests in a time unit than we dequeue. So with time, it grows. So if we're unlucky, and we come to the system at the 2-minute mark, we need to wait until the 1,200 requests before us will be handled first, and then our request will be considered at all.
That looks a lot less bumpy than the previous two diagrams, and that's just because you've changed the scale.
Yeah. I mean, it was GNU plot, not me. But yeah. So sorry for this. So yeah. Okay, what was I saying? Right. So from this, we can learn that we cannot really handle this overload situation when this database slows down just with a queue. It's an unbound queue, just to be clear. Well, just because when someone comes later, you need to wait a lot, until a lot of requests in front will be handled first. So that's one problem we need to solve. Handle the overload somehow. And the second problem we want to solve is that these percentiles I was talking about, this response time quality I was talking about, we need to keep it as low as possible. And as I said, we don't, well, I'm not sure if I said that, but the user service from this previous example cannot really influence this database. It doesn't control when it's slow or not. It also doesn't doesn't influence this consumer, the present service. So how can we control this? It sounds a little bit unfair that we need to handle these two things from this user service that doesn't influence almost anything. But we can just go to the field that's bread and butter is just that, controlling things that we cannot influence. And that field is called control theory, which is a branch of mathematics that tries to solve the control problem. And the control problem is given a dynamic system which changes its output in time. What input should we apply to it so that it generates a desired output, the output that we want? And just to introduce some more terminology, if you ever see a design of a control system, it consists of blocks like this that take some input and generate some output. Looks like a function, slightly. Kind of. Not exactly, because it also contains some state in time. So if we were to implement it in Elixir, and also a plant is a term for the system we want to control in the control theory, just a general name. So if we were to implement in an interface that the component, a single component, so a single block it has an init function that returns an initial state, and then there is a step, takes this initial state, not initial state, the current state, some input, and then generates a new state and the output. Okay, why is it a step, you might ask? Because we're in the digital world, So we cannot really input stuff constantly, and we cannot generate a constant output, a continuous input and output. We just do it at some time intervals. For the rest of this talk, assume 100 milliseconds. So if we add another block to this, we can actually create a legit control system. We have a plant that we control, and we have a controller, not from MVC. We have a controller, so its definition, it's basically a component that controls something. So now the input to our system is the input to the controller, then controller takes it, generates some control action, inputs to the plant, and plant outputs something. And if you consider a real-world example, of that, you can think of yourself driving a car to work, but with a small caveat. You enter the car, you start the engine, you close your eyes, you drive to work, you arrive at your destination, and then you open your eyes. So in this case, input is everything you know about the system that you're going to control, so all the roads, all the things that are happening, what may be on the road. Then you are the controller, control actions are your hands and legs controlling the car, and then plant is the car, and then output is the course the car took. Right, by the way, I don't recommend checking this in practice. Right. If we just do one thing, why is it the real life example, real world example? Because this is something called feed-forward loop, feed-forward control, open loop control. It basically needs to know the input up front. So in every single case, we pre-configure something, and then we hope it will work. This is an example of this. Another example is when you turn on a washing machine for a set program. It will run for 60 minutes, no matter how dirty the clothes are. Now, going back to the driving example, if we just add one more thing here, and this is how in real life driving a car looks like. If we just observe constantly what is the output, so what the course, what the path, what the route the car is taking, and we act accordingly, we will have a feedback loop control. So yeah, this is what's happened really, because you don't close your eyes, you observe the road constantly. If the weather conditions change suddenly, you react. If there are road works, you react, you take the diversion. So yeah. And what's the thing here? Now the input to the whole system is something else. It's not everything we know about the system. It's a set point. So it's a desired value, a desired output of the system. What do we want the system to be output? Now the system, the loop, compares this set point with the last output of the system, and then it generates an error. It's simple as subtracting them, and then this is the input to the controller, and then controller generates control action. Right. If you think about some real-world examples of that, a thermostat or any other air temperature control, cruise control in the car, going back to the car examples, autopilot or instrumented landing system in planes, and from the tech industry, Amazon autoscaling that spins up more instances if the latency goes up. Apple's HTTP live streaming that pushes the video with the bitrate that's the best for your network bandwidth. Redis key eviction if you ever use Redis, if the memory, if you're low in memory, or test-driven development. That's my favorite example. Okay, 1 second, sorry. Cool. Now, let's go back to this unbound queue example. This is something we'll try to, if you remember, the problem in trying to solve is this. We want our service to, one, being protected from overload. Number two, being able to generate responses with a given, within a given service level agreement. Or it's actually service level objective because we don't pay any fines directly to the customer when we miss the deadline. We just have worse user experience. So that's why SLO. But SLA is more popular, I guess. So now imagine this example with the unbound queue, and we'll run some other simulation for the baseline. So now we have 3 queues. Circles on the bottom, there is a dispatch on top, and we generate 300 requests per second. Dispatch just sends it to one of the queues. Doesn't really matter if it's round robin or anything else. So roughly every queue gets 100 requests per second. Now, what's more, every of the queues, we can choose what will be the service time of a request in every single of the queues. So let me explain this. Now the simulation is 60 seconds. Still x-axis. Y-axis this time is the average response time. So this is the time between the request enters the system and leaves the system. So this is the whole time spent in the system as measured by us. And now there are 4 stages in this simulation every 15 seconds. And in the first stage, service time is 5 milliseconds. So we have 3 workers. Every of them can handle 200 requests per second. So we can handle 600 requests per second. And we get 300 requests per second coming in. And the second part, and you can see actually it's also the scale issue. You don't really see the output, the purple output, because it's so good. The response time is so good. In the second frame, we increase the service time by a factor of 2. It's 10 milliseconds, so the service rate exactly matches the number of incoming requests. And you already see the average response time starts to grow because it's exactly the same as incoming rate. The service rate is exactly the same as the incoming rate. So because of the dispatch overhead, we actually service less than 300. And then in the third stage, we increase the service time by a factor of 2 again. Now it's service rate is 150 per second, and you can see how it inflates the average response time. And then in the fourth stage, the response time, service time goes back again, and response time is on the graph. So sorry, service time is how we configure these queues. So what I just want you to remember from this slide, the simulation takes 60 seconds. There are 4 stages. It's good, mostly bad, very bad, good. That's what are the properties of the underlying system, the system we depend on, are in these 4 stages. And this is our baseline, this is naive approach, and we want to improve that. That's the goal. Okay, so let's just think how can we do it with the feedback control loop. You might say right now, well, it's a queue, so let's just bound the queue, and you'll be fine. But just bounding the queue solves only one of these properties, one of these 2 properties I mentioned. It only protects from overload. It doesn't really tell you anything about what will be the output of the system, what will be the average response time. Well, I said it too quickly. Sorry. What will be the timing properties of the response time? So there was an attempt to actually implement it using a feedback loop. It's the same diagram as before, just made more concrete. Now I'll say that. The input, so the set point, the desired value is the average response time. Why average response time, you might ask? Average is not really exactly a good timing indicator. You should be looking at high percentiles. That's what I said before, that's what we do. There are at least 2 reasons for that. First, it's very easy to implement. And number 2, for what we're trying to achieve, it's enough. So for protecting overloads, and well, nobody really told us that it should be 99 percentile, so we just did that. And then we compare it with the actual average response time in the system. So let's say actual average response time is 130 milliseconds. We said the desired average response time is 30 milliseconds, so the error is 100. This is input to the controller. Then controller generates request drop probability, which is not very, very meaningful right now. What I mean is that it will just tell you what amount of requests should be dropped in the next loop iteration. So maybe I forgot to mention that in one of the first slides, that in these two properties, we want to, in this loop, we want to, one, protect from overloads. Number two, we want the average response time to be at 30 milliseconds, but this only applies to the requests that will be handled. If we cannot handle something with this, within this SLA, we'll just tell to the caller, well, sorry, try again later. The service is currently unavailable, or 503. So controller will just say, hey, this is the amount of requests we'll be dropping in the next iteration. And then we have our plant, which is also a new thing here. And what plant does, as you can see, it's called average random drop, but it doesn't really matter. Input is a request drop probability. The output is average response time in this loop execution. So in order to be able to measure that and actually control the request drop, the amount of requests will drop in this iteration, it needs to control all the requests. So it also exposes some API that all requests will go through. If they are to be dropped, it will be dropped by this thing. If they will make the request, if they will be handled, it will be picked to be handled. The response time will be measured by this thing and reported, and then, thanks to this, it can output it. And then in the next loop iteration, we get average response time from the previous iteration. We compare it. We input the error to the controller. Then we get amount of requests that should be dropped. In the next iteration, we get average response time from the iteration that's ending, and so on, and so on, and so on, and so on, and so on. And it works all the time. Yeah. Cool. So yeah, the only thing we need to do now, only thing that's not known here, is the controller. What the controller should do. So we basically need to solve the control problem. That's simple. So what's the simplest thing? So let's say error is this 100 milliseconds I mentioned. So this is the difference between 130 we have, we might have, and 30 we set as a set point. So let's say error is 100 milliseconds. How can we convert this in the most simple way to a drop probability, so a number between 0 and 1? We can multiply it by some magic number. So now it's the controller, our initial implementation of the controller. There's no state, and in every step we just take the input, multiply it by some value, and we output it. And that's it. So let's think. Let's say 100 milliseconds, and we want to generate a drop probability of 1. So this will mean that all the requests will be dropped in the next iteration. So this is 100 times 0, 1, to generate 1, right? So if you remember this slide, this is the baseline. Good, mostly bad, bad, good again. That were the response times in this naive approach with just a queue. So let's test our controller with the magic number equal to 0.1. Now let me explain the graphs here because they're slightly different. X-axis is now number of steps executed in the loop. So since every loop execution happens every 100 milliseconds, we get 600 steps. 60 seconds times 100, times 10, sorry. And we have two graphs. First is the average response time as an output from the feedback loop control. So output from this block thing. And here we have a probability. So this is output from the controller. So this is output from the plant, average random drop. This is output from the controller. And if you see that something's off on this bottom graph, that's definitely the probability. That's value is 45. Doesn't sound like a good probability value to me. So, but the good news is at least it's bound. I mean, the response time, it doesn't go to infinity or to some high numbers. The maximum, as far as I can see, is 500 milliseconds. So that at least solves one problem. It's bound. Let's try to improve it a little bit. If we just try to decrease this magic number a little bit by a factor of 10, it starts looking better. It goes up and down still, but the probability is up to 4. Looks better, but this third section still looks very, very bumpy. So if we decrease it even more, you can see it's tracking this value. I mean, it's less oscillatory. But the problem there is here, in the second part, you can see that the output started to track some different value than our desired 30 milliseconds. I forgot to mention that the red line is 30 milliseconds mark our set point. So we want average response time to be somewhere here. Now, the problem is with just multiplying two numbers like this, like we did, we're not able to make it go down to this red line. We can make it less oscillatory by lowering this number more and more, but we cannot drive it to the red line. What we can do here is we can, instead of, well, in addition to just multiplying two numbers, we can also sum up the error. And because the output oscillates around the set point, with time, the error is positive here, negative here, so this will go to 0, and the whole sum will converge to this difference. I'm not going to go into detail. Why is that? But that's how it works. So now, if we just modified our controller, now it's stateful. Initially, the sum is 0. Sum of error is 0. And now we still multiply it by the magic number 1 we found. But we also multiply our sum of errors by some other magic number and output it. And the new state is the sum of errors. And that's what we did, actually. It's called proportional integral controller, or PI controller. And if we were to find these two magic numbers by trial and error, we might be still here, or at least me, till tomorrow. It actually turns out that this construct is very, very popular in control theory. It controls 80% of things that control theory controls. Actually, it's PID controller, but just for keeping things simple, we consider PI controller here. And there are many analytical and empirical methods to find these two numbers. And let's use one of them. I'm not really going to go into detail very much how it works. But what you do, basically, you take your plant, you apply input, in this case, drop probability of 0, and you measure the output. You run it for some time, you measure it, and the purple line is what you get. And the input was applied at time 0 initially. Because randomness is because of my laptop. What you've got is something called self-regulating process, and you can approximate with an exponential function that the green line or blue line is representing, and it can be described by an exponential function with 3 parameters. it doesn't really matter what they are, but you can count them, and you can apply a formula, and magic number 1 becomes a proportional gain, and magic number 2 becomes integral gain, and these are like this for this case. So now you might ask, well, we just apply it and it will work, right? Not really. Almost. What's very off on this graph is the probability. So in the stable state, everything's fine, everything's totally fine. The first stage, drop probability goes down to some very negative number. And with time, it will go to minus infinity. The thing is that the classical feedback loop tries to keep track exactly of the red line. And, well, we're doing response times. We're below the red line, so that's even better than the red line. So actually, we need to, our desired output is not a value, it's a range between 0 and the red line. And what this means for our controller, it's pretty simple actually. We just cannot integrate when we don't drop anything. So when the output is 0 or less. And if we apply it, then everything looks pretty good. It even oscillates around 30 in both cases. Remember, these are outputs from every single loop iteration. It's a little bumpy. We can do one weird trick, to smoothen the output. It's basically calculating the average of the output over time. And this looks pretty good. And, well, it doesn't track the set point exactly, but here's the third thing. Here's the third reason why the average is good. Remember, again, this is the output from single iteration at interval 100 milliseconds. If we calculate a long-running average response time, we'll just get exactly the red line that I'm going to show you now. This is just the final version of a controller. We just implemented PI controller here as a controller, and we also smoothen things out with an average. Doesn't really matter that much. Just a trick for reducing the noise. Okay, so you might ask, you might say, this is a simulation environment happening on this laptop. Doesn't really mean anything. So we did some real world-like simulations. You'll see 3 examples. Let me try to explain them. It looks pretty bad, right? 3 graphs from left to right. Number of requests handled by the service. Handled, not dropped by the service. Middle graph, number of requests dropped per minute by the service. And the third graph, average response time. There are 2 lines on each of them because there were 2 nodes. So this is the steady state. From the left, we handled 17K requests per minute per node. Just 3 dropped requests. There was a spike probably that we don't see really anywhere else. And average response time is 6 and 8 and 7 milliseconds. So we're good. Now, example 1, exhibit 1, sorry. We increase the load. Let's start from the right this time. Average response time goes up to 120, and then it goes back to 30 milliseconds again. And what happened then? We just increased the load very much. You see number of drop requests, let's say it was 0. It wasn't, but let's say it was at 0. When we increased the load, exactly at 2 a.m., number of drop requests spiked to 150K requests per minute. Now, what happened on the left graph is a little bit concerning because the total number of requests handled dropped as well. Intuitively, I would say it should stay the same. That's what this controller was supposed to do. But, there's a but. We applied so many requests. We're trying to overload the system so much that just getting the requests, just dropping these 150 requests, overloaded the whole system. So so we were able to handle less real requests. So as you can see, it doesn't also react when the database goes slow. It also reacts properly when our machine is overloaded by any reason. And just for completeness, a load decrease, maybe from the center this time. We're dropping number of requests coming into the service 2 times. Number of drop requests drops 2 times. The actual handled number of requests stays the same over time. And then we see these small drops of average response time, and it goes back to 30 milliseconds again. As soon as controller realizes it can handle more within the SLA, basically. Okay, but that was simulation. You might ask, was it actually useful in real life? And it turns out just 3 months after we implemented that, it became useful at least in 2 instances. The first one, holiday time. Last year, the whole meltdown / Spectre havoc, it started like this, that it started for us before everyone knew about it. So it turned out that for no apparent reason, the tail-latencies in one of our systems are just going up without any reason. And the client traffic is the same. Nothing particular happens. It just goes up from the maximum time goes from 15 milliseconds to almost a second. No particular reason. So it took us some time to work around it. It was strangely correlated with Amazon patching things underneath, but we don't have any hard proof that this was the reason. But it took us some time to actually figure out how to work around this. But in the meantime, we had our controller dropping some requests, so this 800 milliseconds didn't become, I don't know, 2 seconds or something. The only reason we dropped so little in this case because average response time was set to 100 milliseconds. But in the real world example number 2, when in one of the internal APIs, we deployed a database call that it turned out to be very inefficient. We run explain. I'll be trying to justify myself slightly. We're running explains, obviously trying to simulate it on Lotus environment with a similar database. It was supposed to take 3 milliseconds. In real life, it took 200. And we were supposed to run 1,000 of them per second. So we could easily overload the database that someone else was using. That's the key point. But we had the controller that protected from actually doing the calls to the database. And what you can see on these graphs actually is the moment when we have our system running inefficiently and then we do a fix and then everything unblocks. So this time, top left, number of requests received by our service. So both dropped and handled. Top right, number of requests handled successfully. Left bottom, number of requests dropped by the service, and then average response time. So we're getting the same number of requests before fix, after fix, but we were handling like 60 of them per minute instead of 60K. And you might ask one more thing. The average response time is 250. Set point was set to 30 milliseconds, so I'm lying probably, or we mistuned our controller. Well, actually, because it was literally no way for this query to complete within 30 milliseconds, what controller was doing, it was just trying to execute one query. It has seen that it takes 200 milliseconds, so started dropping everything. Then it cooled down with time, tried one request, seen it took too long, started dropping everything, cooled down, executed one request, seen that, and so on and so on. And obviously, automatically, it was able to figure out that average response time is back to normal. What else we could use this approach for? Other backend services, everything that has some level of uncertainty. Also on the front end, for a better user experience, We could provide some more lightweight content for lower bandwidth network users, just like Apple did for HLS. Some references here. Feedback Control for Computer Systems by Philip Jannard. I'm just going to say amazing book. And if it's like 80% of it's practical, theories at the end, and you don't need to read it if you want to implement something like that. So it contains like 7 use cases of using feedback loop control for various things. Controlling cache hit ratio, things like that. Then control system lectures on YouTube for free by Brian Douglas. It's classical control theory. No computer science there, but it's very, very comprehensible. And then two articles by Fred Eber I didn't mention in the talk. I was supposed to. About how queues don't fix overload and how you can handle overloads in general. And then some open source libraries you could use. I would like to especially focus on the first one, SBroker. It implements some of the ideas from the control theory. And if you're using Ecto in Elixir, you can use it as a default, not the default, as a dispatch instead of default pull boy. And then discount and jobs. And then it's our article about meltdown spectre thing, if you wish. This will be available, so there are links. That was it. Questions?